I'm sorry that I left you with a cliffhanger at the end of the last video. Now we're going to look at a little more interpretation you can do with microbenchmarks, and you're going to answer the question that I posted at the end of the video, which is, what is the associativity of this architecture? And I claim it was a fully associative TLB in this architecture. Otherwise, the curves wouldn't drop like this. And the reason I say that is that I can see that for 4 kilobytes we have problem with a TLB reach, but already at 8 kilobytes this curve starts dropping down. So what's happening at 8 kilobytes strides is that we will start to fit enough translations in the TLB that we no longer have a problem with the TLB. And so on. And based on that assumption here that, going from 4 kilobytes to 8 kilobytes, we suddenly will start to fit all the translations we need for this vector in the TLB, tells me that this ought to be a fully associative TLB. And this is why. So remembering all these parameters here of the cache that we designed, I took those parameters and I designed exactly the same kind of cache. So we have an 8 kilobyte. Actually, the first level cache is different than a previous example, but that doesn't matter. We have an 8 kilobyte two-way set associative cache. Cache line is 32 bytes. Word size is 4 bytes. And the page size is 4 kilobytes here. Okay. And page size 4 kilobyte implies that the 12 least significant bits of the address will not change when we make a translation from virtual to physical. So when we do a VIPT, virtually indexed physically tagged TLB design or cache design, then we know that we can use any of the bits here, or these 12 bits, to index into the virtually indexed cache, because bits don't change when we make the physical. Okay, so that's cool, and we know the bits that identify a byte within a word, and we know the number of bits that identifies a word within a cache line, so we need to use them to drive the multiplexer. And then it's a two-way set associative cache, so we need some kind of comparisons going on here to produce this fourth bit that's going to drive the multiplexer 16:1 to produce the data that's requested. So this, we all know this. And we also know that you need to put a TLB right next to this. So if the TLB has the same design parameters as in the previous example, 5 and 12 entries, and let's assume it's a set associative cache. Then, for example, if it's a two-way set associative cache, then we will need 512 sets, where each set contains 2 entries, the left entry and the right entry, because it's a two-way set associative cache. So each entry contains a virtual address tag and contains the physical address page frame that later will be used to compare with these physical address tags that resides in the cache. We have a 2-to-1 multiplexer to pick the right entry we're interested in. And since this is a 256 entry cache, we need exactly 8 bits to index into this cache, this TLB cache over here. And we take the next 8 bits to index into the cache, just as we did when into the TLB, just as we did when we designed the cache. We use lower level bits to index into as index bits. Same thing for the TLB. So we use these bits as index bits, 8 of them, and we uniquely find 1 out of 256 sets in this TLB. And the translation we're looking for is either in the left or in the right, or it's not in the TLB at all. We use those bits, and whatever bits we haven't used so far, the 12 bits, will be used to compare with the virtual address tag stored in the TLB. And if it's a match, one, this logic will choose left or right, and the page table entry there containing the physical address upper bits, those 20 bits will be compared with the 20 bits stored here, and so on. Well, we all know this. This is exactly the cache we designed in previous lectures. But a very interesting property here is, the property when we have a stride of 4 kilobytes. That's when we had problem with the TLB. So when we make an access with 4 kilobytes, we access each page exactly once. Okay, so we're going to access all the pages once. We're going to fill the TLB, and then we're going to keep, since the vector is so large, we're going to keep putting new entries in the TLB, kicking all entries out. So when we get back to the beginning of the vector again, we will not find the translation that we're interested in this vector. And then in the previous graph, we saw that if we take strides of 8 kilobytes instead, then we use every second page of the vector, which means we only need half as many TLB entries. And when we and that made the average latency drop when we used 8 kilobytes. And based on that observation, I say that this TLB cannot be a set-associative cache because, for example, in this way, two-way set-associative cache, one property that holds if you take strides of 8 kilobytes is that this bit here will always be the same. All the strides you take, this bit will be exactly the same because it's 8 kilobytes. Even 8 kilobyte strides, which means that this bit will not change, all the upper bits here will change. That means that since we use this bit as part of the index function, that means we'll use every other set in this TLB. So yes, we will only need translation for half as many pages, but on the other hand, since this bit doesn't change and we use it as an index function, that means we use every other set, which means that the number of entries we use in the TLB is cut in half. So we need half as many entries as for 4 kilobytes, but for 8 kilobytes we only use every other entry in the TLB, which means that our effective TLB reach will not get any larger. So how would this picture change if I told you that the TLB used here is a set-associative cache? Sorry, the TLB used is a set-associative TLB. Well, that means that going beyond 4 kilobytes to 8 kilobytes is not going to help you anything. You need half as many translations, but you're only going to use half as many of the entries in the TLB. So it comes out at a wash. So what's changing here is that you're not going to see any drop in the TLB when you start to use larger strides than the page. There are lots of interesting questions you can ask yourself, and this is a very good exam question because if you can interpret a curve like this, if you can have enough understanding of how to reverse engineer a cache from this curve, I claim that you fully understand how caches work as well as how TLB works. And if you understand how this curve looks, then you would understand why it's a bad idea to have an 8 kilobyte stride in your application if the TLB is a set-associative TLB. And with that knowledge, you will be able to write programs that runs with, maybe on average a nanosecond, a couple of nanosecond access time to memory, rather than programs that runs with average access time of 130 nanoseconds to the data. Another question, very good exam question, is to have a picture like this and ask lots of what-if questions. So this is just one possible what-if questions. So what if, in this picture here, what would change in this picture if we change the L2 size, L2 cache size from 1 megabyte to 2 megabytes? Take a few seconds to think about that, and I'll give away the answer. Well, suddenly all these accesses here would fit in the second level cache. So instead of experiencing a memory latency here, we would experience a L2 cache hit for these accesses as well. So what would happen here would be that the 2 megabyte access would move down to the other L2 hits, and this curve here would completely disappear from the face of the moon. What we're going to do in class is to look at a curve that looks like this, slightly different shape, and we will discuss what kind of memory system it's hidden behind this kind of macro benchmark signature. Take a look at this and think about that before we meet in class.